Andromeda Galaxy. The Andromeda Galaxy is a barred spiral galaxy and is the nearest major galaxy to the Milky Way. It was originally named the Andromeda Nebula and is catalogued as Messier 31, M31, and NGC 224. Andromeda has a d25 isophotral diameter of about 46.56 kiloparsecs, 152,000 light-years, and is approximately 765 kpc, 2.5 million light-years, from Earth. The galaxy's name stems from the area of Earth's sky in which it appears, the constellation of Andromeda, which itself is named after the princess who was the wife of Perseus in Greek mythology. The virial mass of the Andromeda Galaxy is of the same order of magnitude as that of the Milky Way, at 1 trillion solar masses, 2.0 times 1042 kilograms. The mass of either galaxy is difficult to estimate with any accuracy, but it was long thought that the Andromeda Galaxy was more massive than the Milky Way by a margin of some 25% to 50%. However, this has been called into question by early 21st century studies indicating a possibly lower mass for the Andromeda Galaxy and a higher mass for the Milky Way. The Andromeda Galaxy has a diameter of about 46.56 kpc, 152,000 light-years, making it the largest member of the local group of galaxies in terms of extension. The Milky Way and Andromeda galaxies are expected to collide with each other in around 4 to 5 billion years, merging to potentially form a giant elliptical galaxy or a large lenticular galaxy. With an apparent magnitude of 3.4, the Andromeda Galaxy is among the brightest of the Messier objects, and is visible to the naked eye from Earth on moonless nights, even when viewed from areas with moderate light pollution. Observation history. The Andromeda Galaxy is visible to the naked eye in dark skies. Around the year 964 CE, the Persian astronomer Robert al-Rahman al-Sufi described the Andromeda Galaxy in his Book of Fixed Stars as a nebulous smear or small cloud. Star charts of that period labeled it as the Little Cloud. In 1612, the German astronomer Simon Marius gave an early description of the Andromeda Galaxy based on telescopic observations. Pierre-Louis Maupertuis conjectured in 1745 that the blurry spot was an island universe. Charles Messier catalogued Andromeda as object M31 in 1764 and incorrectly credited Marius as the discoverer despite its being visible to the naked eye. In 1785, the astronomer William Herschel noted a faint reddish hue in the core region of Andromeda. He believed Andromeda to be the nearest of all the great nebulae, and based on the color and magnitude of the nebula, he incorrectly guessed that it was no more than 2,000 times the distance of Sirius, or roughly 18,000 light-years, 5.5 kpc. In 1850, William Parsons, 3rd Earl of Rosse, made a drawing of Andromeda's spiral structure. In 1864, William Huggins noted that the spectrum of Andromeda differed from that of a gaseous nebula. The spectrum of Andromeda displays a continuum of frequencies, superimposed with dark absorption lines that help identify the chemical composition of an object. Andromeda's spectrum is very similar to the spectra of individual stars, and from this, it was deduced that Andromeda has a stellar nature. In 1885, a supernova, known as S Andromedae, was seen in Andromeda, the first and so far only one observed in that galaxy. At the time, it was called Nova 1885. The difference between novae in the modern sense and supernovae was not yet known. Andromeda was considered to be a nearby object, and it was not realized that the nova was much brighter than ordinary novae. In 1888, Isaac Roberts took one of the first photographs of Andromeda, which was still commonly thought to be a nebula within our galaxy. Roberts mistook Andromeda and similar spiral nebulae as star systems being formed. In 1912, Vesto Slipher used spectroscopy to measure the radial velocity of Andromeda with respect to the Solar System, the largest velocity yet measured, at 300 km per second, 190 miles per second. Island Universes Hypothesis. As early as 1755, the German philosopher Immanuel Kant proposed the hypothesis that the Milky Way is only one of many galaxies in his book Universal Natural History and Theory of the Heavens. arguing that a structure like the Milky Way would look like a circular nebula viewed from above and like an ellipsoid if viewed from an angle. He concluded that the observed elliptical nebulae like Andromeda, which could not be explained otherwise at the time, were indeed galaxies similar to the Milky Way, not a nebula, as Andromeda was commonly believed to be. In 1917, Heber Curtis observed a nova within Andromeda. After searching the photographic record, 11 more novae were discovered. Curtis noticed that these novae were, on average, 10 magnitudes fainter than those that occurred elsewhere in the sky. As a result, he was able to come up with a distance estimate of 500,000 light-years, 3.2 times 1010 astronomical units. Although this estimate is about 5-fold lower than the best estimates now available, it was the first known estimate of the distance to Andromeda that was correct to the order of magnitude, i.e., it was correct to within a factor of 10 of the current high-accuracy estimates, which placed the distance around 2.5 million light-years. Curtis became a proponent of the so-called island universes hypothesis, that spiral nebulae were actually independent galaxies. In 1920, the great debate between Harlow Shapley and Curtis took place concerning the nature of the Milky Way, spiral nebulae, and the dimensions of the universe. To support his claim of the Great Andromeda Nebula being, in fact, an external galaxy, Curtis also noted the appearance of dark lanes within Andromeda that resembled the dust clouds in our own galaxy, as well as historical observations of the Andromeda Galaxy's significant Doppler shift. In 1922, Ernst Opik presented a method to estimate the distance of Andromeda using the measured velocities of its stars. His result placed the Andromeda Nebula far outside our galaxy at a distance of about 450 kpc, 1,500 kilo-light-years. Edwin Hubble settled the debate in 1925 when he identified extragalactic Cepheid variable stars for the first time on astronomical photos of Andromeda. These were made using the 100-inch, 2.5 meters, Hooker telescope, and they enabled the distance of the Great Andromeda Nebula to be determined. His measurement demonstrated conclusively that this feature was not a cluster of stars and gas within our own galaxy, but an entirely separate galaxy located a significant distance from the Milky Way. In 1943, Walter Baade was the first person to resolve stars in the central region of the Andromeda Galaxy. Baade identified two distinct populations of stars based on their metallicity, naming the young, high-velocity stars in the disk type I and the older, red stars in the bulge type II. This nomenclature was subsequently adopted for stars within the Milky Way, and elsewhere. The existence of two distinct populations had been noted earlier by Jan Nort. Baade also discovered that there were two types of Cepheid variable stars, which resulted in a doubling of the distance estimate to Andromeda, as well as the remainder of the universe. In 1950, radio emissions from the Andromeda Galaxy were detected by Robert Hanbury Brown and Cyril Hazard at the Jodrell Bank Observatory. The first radio maps of the galaxy were made in the 1950s by John Baldwin and collaborators at the Cambridge Radio Astronomy Group. The core of the Andromeda Galaxy is called 2C56 in the 2C Radio Astronomy Catalogue. In 2009, an occurrence of microlensing, a phenomenon caused by the deflection of light by a massive object, may have led to the first discovery of a planet in the Andromeda Galaxy. In 2020, observations of linearly polarized radio emission with the Westerbork Synthesis Radio Telescope, the Effelsburg 100-meter radio telescope, and the Very Large Array revealed ordered magnetic fields aligned along the 10 kpc ring of gas and star formation. General. The estimated distance of the Andromeda Galaxy from our own was doubled in 1953 when it was discovered that there is another, dimmer type of Cepheid variable star. In the 1990s, measurements of both standard red giants as well as red clump stars from the Hipparcos satellite measurements were used to calibrate the Cepheid distances. Formation and history. A major merger occurred 2 to 3 billion years ago at the Andromeda location, involving two galaxies with a mass ratio of approximately 4. The discovery of recent merger in the Andromeda Galaxy was first based on interpreting its anomalous age-velocity dispersion relation, as well as the fact that 2 billion years ago, star formation throughout Andromeda's disk was much more active than today. Modeling of this violent collision shows that it has formed most of the galaxy's metal-rich, galactic halo, including the giant stream, and also the extended thick disk, the young age-thin disk, and the static 10 kpc ring. During this epoch, its rate of star formation would have been very high, to the point of becoming a luminous infrared galaxy for roughly 100 million years. Modeling also recovers the bulge profile, the large bar, and the overall halo density profile. Andromeda and the Triangulum Galaxy, M33, might have had a very close passage 2 to 4 billion years ago, but it seems unlikely from the last measurements from the Hubble Space Telescope. Distance estimate. At least 4 distinct techniques have been used to estimate distances from Earth to the Andromeda Galaxy. In 2003, using the infrared surface brightness fluctuations, ISBF, and adjusting for the new period luminosity value and a metallicity correction of -0.2 mag-1 in OH, an estimate of 2.57 ±0.06 million light-years, 1.625 times 1011 ±3.8 times 109 astronomical units, was derived. A 2004 Cepheid variable method estimated the distance to be 2.51 ±0.13 million light-years, 770 ±40 kpc. In 2005, an eclipsing binary star was discovered in the Andromeda Galaxy. The binary is made up of 2 hot blue stars of types O and B. By studying the eclipses of the stars, astronomers were able to measure their sizes. Knowing the sizes and temperatures of the stars, they were able to measure their absolute magnitude. When the visual and absolute magnitudes are known, the distance to the star can be calculated. The stars lie at a distance of 2.52 times 106 ±0.14 times 106 light-years, 1.594 times 1011 ±8.9 times 109 astronomical units, and the whole Andromeda Galaxy at about 2.5 times 106 light-years, 1.6 times 1011 astronomical units. This new value is in excellent agreement with the previous, independent Cepheid-based distance value. The TRGB method was also used in 2005, giving a distance of 2.56 times 106 ±0.08 times 106 light-years, 1.619 times 1011 ±5.1 times 109 astronomical units. Averaged together, these distance estimates give a value of 2.54 times 106 ±0.11 times 106 light-years, 1.606 times 1011 ±7.0 times 109 astronomical units. Mass estimates. Until 2018, mass estimates for the Andromeda Galaxy's halo, including dark matter, gave a value of approximately 1.5 times 1012 m, compared to 8 times 1011 m for the Milky Way. This contradicted even earlier measurements that seemed to indicate that the Andromeda Galaxy and Milky Way are almost equal in mass. In 2018, the earlier measurements for equality of mass were re-established by radio results as approximately 8 times 1011 m. In 2006, the Andromeda Galaxy's spheroid was determined to have a higher stellar density than that of the Milky Way, and its galactic stellar disk was estimated at twice the diameter of that of the Milky Way. The total mass of the Andromeda Galaxy is estimated to be between 8 times 1011 m and 1.1 times 1012 m. The stellar mass of M31 is 10 to 15 times 1010 m, with 30% of that mass in the central bulge, 56% in the disk, and the remaining 14% in the stellar halo. The radio results, similar mass to the Milky Way galaxy, should be taken as likeliest as of 2018, although clearly, This matter is still under active investigation by several research groups worldwide. As of 2019, current calculations based on escape velocity and dynamical mass measurements put the Andromeda Galaxy at 0.8 times 1012 m, which is only half of the Milky Way's newer mass, calculated in 2019, at 1.5 times 1012 m. In addition to stars, the Andromeda Galaxy's interstellar medium contains at least 7.2 times 109 m in the form of neutral hydrogen, at least 3.4 times 108 m as molecular hydrogen, within its innermost 10 kiloparsecs, and 5.4 times 107 m of dust. The Andromeda Galaxy is surrounded by a massive halo of hot gas that is estimated to contain half the mass of the stars in the galaxy. The nearly invisible halo stretches about 1 million light-years from its host galaxy, halfway to our Milky Way galaxy. Simulations of galaxies indicate the halo formed at the same time as the Andromeda Galaxy. The halo is enriched in elements heavier than hydrogen and helium, formed from supernovae, and its properties are those expected for a galaxy that lies in the green valley of the galaxy color magnitude diagram, see below. Supernovae erupt in the Andromeda Galaxy's star-filled disk and eject these heavier elements into space. Over the Andromeda Galaxy's lifetime, nearly half of the heavy elements made by its stars have been ejected far beyond the galaxy's 200,000 light-year diameter stellar disk. Luminosity estimates. Compared to the Milky Way, the Andromeda Galaxy appears to have predominantly older stars with ages greater than 7 times 109 years. The estimated luminosity of the Andromeda Galaxy, 2.6 times 1010 liters, is about 25% higher than that of our own galaxy. However, the galaxy has a high inclination as seen from Earth, and its interstellar dust absorbs an unknown amount of light, so it is difficult to estimate its actual brightness, and other authors have given other values for the luminosity of the Andromeda Galaxy. Some authors even propose it is the second brightest galaxy within a radius of 10 megaparsecs of the Milky Way, after the Sombrero Galaxy, with an absolute magnitude of around -22.21 or close. An estimation done with the help of Spitzer Space Telescope published in 2010 suggests an absolute magnitude, in the blue, of -20.89, that with a color index of +0.63 translates to an absolute visual magnitude of -21.52, compared to -20.9 for the Milky Way, and a total luminosity in that wavelength of 3.64 times 1010 liters. The rate of star formation in the Milky Way is much higher, with the Andromeda Galaxy producing only about 1 solar mass per year compared to 3 to 5 solar masses for the Milky Way. The rate of novae in the Milky Way is also double that of the Andromeda Galaxy. This suggests that the latter once experienced a great star formation phase, but is now in a relative state of quiescence, whereas the Milky Way is experiencing more active star formation. Should this continue, the luminosity of the Milky Way may eventually overtake that of the Andromeda Galaxy. According to recent studies, the Andromeda Galaxy lies in what is known in the galaxy color magnitude diagram as the Green Valley, a region populated by galaxies like the Milky Way in transition from the blue cloud, galaxies actively forming new stars, to the red sequence, galaxies that lack star formation. Star formation activity in Green Valley galaxies is slowing as they run out of star-forming gas in the interstellar medium. In simulated galaxies with similar properties to the Andromeda Galaxy, star formation is expected to extinguish within about 5 billion years, even accounting for the expected, short-term increase in the rate of star formation due to the collision between the Andromeda Galaxy and the Milky Way. Structure. Based on its appearance in visible light, the Andromeda Galaxy is classified as an SA/SB galaxy in the de Vaucouleurs-Sandage extended classification system of spiral galaxies. However, infrared data from the 2-mass survey and the Spitzer Space Telescope showed that Andromeda is actually a barred spiral galaxy, like the Milky Way, with Andromeda's bar major axis oriented 55 degrees anti-clockwise from the disk major axis. There are various methods used in astronomy in defining the size of a galaxy, and each method can yield different results concerning one another. The most commonly employed is the D25 standard, the isophote where the photometric brightness of a galaxy in the B band, 445 nanometers wavelength of light, in the blue part of the visible spectrum, reaches 25 mag/arcsec2. The third reference catalogue of bright galaxies, RC3, used this standard for Andromeda in 1991, yielding an isophotal diameter of 46.56 kiloparsecs, 152,000 light-years, at a distance of 2.5 million light-years. An earlier estimate from 1981 gave a diameter for Andromeda at 54 kiloparsecs, 176,000 light-years. A study in 2005 by the Keck telescopes shows the existence of a tenuous sprinkle of stars, or galactic halo, extending outward from the galaxy. The stars in this halo behave differently from the ones in Andromeda's main galactic disk, where they show rather disorganized orbital motions as opposed to the stars in the main disk having more orderly orbits and uniform velocities of 200 km per second. This diffuse halo extends outwards away from Andromeda's main disk with the diameter of 67.45 kiloparsecs, 220,000 light-years. The galaxy is inclined an estimated 77 degrees relative to Earth, where an angle of 90 degrees would be edge-on. Analysis of the cross-sectional shape of the galaxy appears to demonstrate a pronounced, S-shaped warp, rather than just a flat disk. A possible cause of such a warp could be gravitational interaction with the satellite galaxies near the Andromeda Galaxy. The galaxy M33 could be responsible for some warp in Andromeda's arms, though more precise distances and radial velocities are required. Spectroscopic studies have provided detailed measurements of the rotational velocity of the Andromeda Galaxy as a function of radial distance from the core. The rotational velocity has a maximum value of 225 km per second, 140 miles per second, at 1,300 light-years, 82 million astronomical units, from the core, and it has its minimum possibly as low as 50 km per second, 31 miles per second, at 7,000 light-years, 440 million astronomical units, from the core. Further out, rotational velocity rises out to a radius of 33,000 light-years, 2.1 times 109 astronomical units, where it reaches a peak of 250 km per second, 160 miles per second. The velocities slowly decline beyond that distance, dropping to around 200 km per second, 120 miles per second, at 80,000 light-years, 5.1 times 109 astronomical units. These velocity measurements imply a concentrated mass of about 6 times 109 m in the nucleus. The total mass of the galaxy increases linearly out to 45,000 light-years, 2.8 times 109 astronomical units, then more slowly beyond that radius. The spiral arms of the Andromeda Galaxy are outlined by a series of high regions, first studied in great detail by Walter Bod and described by him as resembling beads on a string. His studies show two spiral arms that appear to be tightly wound, although they are more widely spaced than in our galaxy. His descriptions of the spiral structure, as each arm crosses the major axis of the Andromeda Galaxy, are as follows: Section pp 1062 Section pp 92: Since the Andromeda Galaxy is seen close to edge-on, it is difficult to study its spiral structure. Rectified images of the galaxy seem to show a fairly normal spiral galaxy, exhibiting two continuous trailing arms that are separated from each other by a minimum of about 13,000 light-years, 820 million astronomical units, and that can be followed outward from a distance of roughly 1,600 light-years, 100 million astronomical units, from the core. Alternative spiral structures have been proposed, such as a single spiral arm or a flocculent pattern of long, filamentary, and thick spiral arms. The most likely cause of the distortions of the spiral pattern is thought to be interaction with galaxy satellites M32 and M110. This can be seen by the displacement of the neutral hydrogen clouds from the stars. In 1998, images from the European Space Agency's Infrared Space Observatory demonstrated that the overall form of the Andromeda Galaxy may be transitioning into a ring galaxy. The gas and dust within the galaxy are generally formed into several overlapping rings, with a particularly prominent ring formed at a radius of 32,000 light-years, 9.8 kpc, from the core, nicknamed by some astronomers the Ring of Fire. This ring is hidden from visible light images of the galaxy because it is composed primarily of cold dust, and most of the star formation that is taking place in the Andromeda Galaxy is concentrated there. Later studies with the help of the Spitzer Space Telescope showed how the Andromeda Galaxy's spiral structure in the infrared appears to be composed of two spiral arms that emerge from a central bar and continue beyond the large ring mentioned above. Those arms, however, are not continuous and have a segmented structure. Close examination of the inner region of the Andromeda Galaxy with the same telescope also showed a smaller dust ring that is believed to have been caused by the interaction with M32 more than 200 million years ago. Simulations show that the smaller galaxy passed through the disk of the Andromeda Galaxy along the latter's polar axis. This collision stripped more than half the mass from the smaller M32 and created the ring structures in Andromeda. It is the coexistence of the long-known large ring-like feature in the gas of Messier 31, together with this newly discovered inner ring-like structure, offset from the barycenter, that suggested a nearly head-on collision with the satellite M32, a milder version of the cartwheel encounter. Studies of the extended halo of the Andromeda Galaxy show that it is roughly comparable to that of the Milky Way, with stars in the halo being generally metal-poor, and increasingly so with greater distance. This evidence indicates that the two galaxies have followed similar evolutionary paths. They are likely to have accreted and assimilated about 100 to 200 low-mass galaxies during the past 12 billion years. The stars in the extended halos of the Andromeda Galaxy and the Milky Way may extend nearly one-third the distance separating the two galaxies. Nucleus. The Andromeda Galaxy is known to harbor a dense and compact star cluster at its very center, similar to our own galaxy. A large telescope creates a visual impression of a star embedded in the more diffuse surrounding bulge. In 1991, the Hubble Space Telescope was used to image the Andromeda Galaxy's inner nucleus. The nucleus consists of two concentrations separated by 1.5 pc, 4.9 light-years. The brighter concentration, designated as P1, is offset from the center of the galaxy. The dimmer concentration, P2, falls at the true center of the galaxy and contains an embedded star cluster, called P3, containing many UV bright A stars and the supermassive black hole, called M31. The black hole is classified as a low luminosity AGN, LAGN, and it was detected only in radio wavelengths and in X-rays. It was quiescent in 2004 to 2005, but it was highly variable in 2006 to 2007. The mass of M31 was measured at 3 to 5 times 107 m in 1993, and at 1.1 to 2.3 times 108 m in 2005. The velocity dispersion of material around it is measured to be 160 km per second, 100 miles per second. It has been proposed that the observed double nucleus could be explained if P1 is the projection of a disk of stars in an eccentric orbit around the central black hole. The eccentricity is such that stars linger at the orbital upper center, creating a concentration of stars. It has been postulated that such an eccentric disk could have been formed from the result of a previous black hole merger, where the release of gravitational waves could have kicked the stars into their current eccentric distribution. P2 also contains a compact disk of hot, spectral class A stars. The A stars are not evident in radar filters, but in blue and ultraviolet light they dominate the nucleus, causing P2 to appear more prominent than P1. While at the initial time of its discovery it was hypothesized that the brighter portion of the double nucleus is the remnant of a small galaxy cannibalized by the Andromeda Galaxy, this is no longer considered a viable explanation, largely because such a nucleus would have an exceedingly short lifetime due to tidal disruption by the central black hole. While this could be partially resolved if P1 had its own black hole to stabilize it, the distribution of stars in P1 does not suggest that there is a black hole at its center. Discrete sources. Apparently, by late 1968, no X-rays had been detected from the Andromeda Galaxy. A balloon flight on the 20th of October 1970, set an upper limit for detectable hard X-rays from the Andromeda Galaxy. The Swift-Bat All-Sky survey successfully detected hard X-rays coming from a region centered 6 arcseconds away from the galaxy center. The emission above 25 kilo-electron-volts was later found to be originating from a single source named 3XMMJ004232.1 plus 411314, and identified as a binary system where a compact object, a neutron star or a black hole, accretes matter from a star. Multiple X-ray sources have since been detected in the Andromeda Galaxy, using observations from the European Space Agency's ESA, XMM Newton Orbiting Observatory. Robin Barnard et al. Hypothesized that these are candidate black holes or neutron stars, which are heating the incoming gas to millions of kelvins and emitting X-rays. Neutron stars and black holes can be distinguished mainly by measuring their masses. An observation campaign of New Star space mission identified 40 objects of this kind in the galaxy. In 2012, a microquasar, a radio burst emanating from a smaller black hole, was detected in the Andromeda Galaxy. The progenitor black hole is located near the galactic center and has about 10 m. It was discovered through data collected by the European Space Agency's XMM Newton probe and was subsequently observed by NASA's Swift Gamma Ray Burst mission and Chandra X-ray Observatory, the Very Large Array, and the Very Long Baseline Array. The microquasar was the first observed within the Andromeda Galaxy and the first outside of the Milky Way galaxy. Globular clusters. There are approximately 460 globular clusters associated with the Andromeda Galaxy. The most massive of these clusters, identified as Mayall 2, nicknamed Globular 1, has a greater luminosity than any other known globular cluster in the local group of galaxies. It contains several million stars and is about twice as luminous as Omega Centauri, the brightest known globular cluster in the Milky Way. Globular 1, or G1, has several stellar populations and a structure too massive for an ordinary globular. As a result, some consider G1 to be the remnant core of a dwarf galaxy that was consumed by Andromeda in the distant past. The globular with the greatest apparent brightness is G76, which is located in the southwest arm's eastern half. Another massive globular cluster, named O37b327 and discovered in 2006 as is heavily reddened by the Andromeda Galaxy's interstellar dust, was thought to be more massive than G1 and the largest cluster of the local group. However, other studies have shown it is actually similar in properties to G1. Unlike the globular clusters of the Milky Way, which show a relatively low age dispersion, Andromeda Galaxy's globular clusters have a much larger range of ages, from systems as old as the galaxy itself to much younger systems, with ages between a few 100 million years to 5 billion years. In 2005, astronomers discovered a completely new type of star cluster in the Andromeda Galaxy. The newfound clusters contain hundreds of thousands of stars, a similar number of stars that can be found in globular clusters. What distinguishes them from the globular clusters is that they are much larger, several hundred light-years across, and hundreds of times less dense. The distances between the stars are, therefore, much greater within the newly discovered extended clusters. The most massive globular cluster in the Andromeda Galaxy, BO23G078, likely has a central intermediate black hole of almost 100,000 solar masses. PA99N2 event and possible exoplanet in galaxy. PA99N2 was a micro-lensing event detected in the Andromeda Galaxy in 1999. One of the explanations for this is the gravitational lensing of a red giant by a star with a mass between 0.02 and 3.6 times that of the Sun, which suggested that the star is likely orbited by a planet. This possible exoplanet would have a mass 6.34 times that of Jupiter. If finally confirmed, it would be the first ever found extragalactic planet. However, anomalies in the event were later found. Nearby and satellite galaxies. Like the Milky Way, the Andromeda Galaxy has smaller satellite galaxies, consisting of over 20 known dwarf galaxies. The Andromeda Galaxy's dwarf galaxy population is very similar to the Milky Way's, but the galaxies are much more numerous. The best known and most readily observed satellite galaxies are M32 and M110. Based on current evidence, it appears that M32 underwent a close encounter with the Andromeda Galaxy in the past. M32 may once have been a larger galaxy that had its stellar disk removed by M31 and underwent a sharp increase of star formation in the core region, which lasted until the relatively recent past. M110 also appears to be interacting with the Andromeda Galaxy, and astronomers have found in the halo of the latter a stream of metal-rich stars that appear to have been stripped from these satellite galaxies. M110 does contain a dusty lane, which may indicate recent or ongoing star formation. M32 has a young stellar population as well. The Triangulum Galaxy is a non-dwarf galaxy that lies 750,000 light-years from Andromeda. It is currently unknown whether it is a satellite of Andromeda. In 2006, it was discovered that 9 of the satellite galaxies lie in a plane that intersects the core of the Andromeda Galaxy. They are not randomly arranged as would be expected from independent interactions. This may indicate a common tidal origin for the satellites. Collision with the Milky Way. The Andromeda Galaxy is approaching the Milky Way at about 110 kilometers, 68 miles, per second. It has been measured approaching relative to the Sun at around 300 kilometers per second, 190 miles per second, as the Sun orbits around the center of the galaxy at a speed of approximately 225 kilometers per second, 140 miles per second. This makes the Andromeda Galaxy one of about 100 observable blue-shifted galaxies. Andromeda Galaxy's tangential or sideways velocity concerning the Milky Way is relatively much smaller than the approaching velocity, and therefore it is expected to collide directly with the Milky Way in about 2.5 to 4 billion years. A likely outcome of the collision is that the galaxies will merge to form a giant elliptical galaxy or possibly large disk galaxy. Such events are frequent among the galaxies in galaxy groups. The fate of Earth and the Solar System in the event of a collision is currently unknown. Before the galaxies merge, there is a small chance that the Solar System could be ejected from the Milky Way or join the Andromeda Galaxy. Amateur observation. Under most viewing conditions, the Andromeda Galaxy is one of the most distant objects that can be seen with the naked eye, due to its sheer size. M33 and, for observers with exceptionally good vision, M81 can be seen under very dark skies. The galaxy is commonly located in the sky about the constellations Cassiopeia and Pegasus. Andromeda is best seen during autumn nights in the northern hemisphere when it passes high overhead, reaching its highest point around midnight in October, and 2 hours earlier each successive month. In the early evening, it rises in the east in September and sets in the west in February. From the southern hemisphere, the Andromeda Galaxy is visible between October and December, best viewed from as far north as possible. Binoculars can reveal some larger structures of the galaxy and its 2 brightest satellite galaxies, M32 and M110. An amateur telescope can reveal Andromeda's disk, some of its brightest globular clusters, dark dust lanes, and the large star cloud NGC 206.